Good afternoon. My name is Lianying Zhao, an associate professor at Carleton University, Canada. I'm going to present our paper on TLS certificate validation issues, which is a joint work between Concordia University, Canada, and Carleton University. Unfortunately, our student authors are not able to make it here due to visa issues. All right, so the purpose of this project was originally about study on the TLS certificate validation issues in Android apps. Because we all know the security of the app's communication is anchored in the proper validation of the certificate presented by the server. But this is not something new, and there's been a lot of prior work on this with problems identified. But what's been missing in the prior work is a fine-grained attribution of the identified problems. Or put another way, the apps were just considered to be monolithic. For example, if we see an insecure connection because of validation issues, we simply say that app is insecure. Or is the developer of the app to blame? This does not distinguish the potentially multiple parties in a single app. So by saying multiple parties, I'm already alluding to my next point, which is, again, not so new situation that, as mentioned in the first talk as well, developers will not start from scratch when writing an app, right? Usually an APK, the Android APK includes multiple libraries, third-party libraries, also known as SDKs, for multiple purposes. For example, we have Tencent Bugly for bug reporting or statistic collection, and Google AdMob for ads management within the app to earn income, and many more. So this is already reflected in the recent Android privacy sandbox introduced in Android 13, which uses the SDK runtime to isolate individual third-party SDKs so that they don't see each other, they don't access resources from each other. And when this is applied to the attribution of the identified certificate validation problems, we should expect something like this. So if you have an insecure connection, we have to identify which specific library, like library 1, library 2, or the app itself introduces this issue. But that's not straightforward either, as we'll show very shortly, because whoever initiated the insecure connection might not be the one to blame, because it could be another party that validated a certificate for that connection. So at the high level, the contributions of this paper is twofold. First, we developed a tool called Marvin that does this fine-grained attribution of the identified certificate validation problems. And second, surprisingly, during this process, we found a phenomenon we call certificate validation hijacking, which means, as I just mentioned, it's someone's connection certificate gets validated by someone else unknowingly, sometimes even insecurely. Before we talk about the details, I'll quickly go over the certificate validation issues we consider in scope. So there are certificate signatures just skipped, not verified, and there are self-signed certificates, there are expired certificates, and there's also domain mismatch, which means it's the wrong host, not the one the certificate was issued to. And correspondingly, in the code, there are classes and their methods taking care of such checks. For example, there's the hostname verifier class with the method verify that checks for the domain mismatch problem. And there are also other, for example, the trust manager class taking care of the rest of the checks with the check server trusted, or if it's mutual authentication, there's also check client trusted. So with that in mind, we can look at the old workflow of Marvin. So basically, we man the middle of the track for each app on the network side, and then replace the original certificate with one of the issues I just mentioned. And then if the connection is established, meaning it is insecure, it will be placed in the pool for further analysis. Otherwise, we'll just revert the original certificate and then let it just pass through because it is secure. Obviously, we also need to do something on the phone to ensure maximum coverage of the connections and then see what's happening within the app. So we control the UI interaction of each app, and then we use Frida to hook necessary validation functions so that we can collect stack traces locally, and then we correlate them with the traffic collected from the network side. And then we can determine multiple things, for example, first-party versus third-party code using some heuristics, such as if a package name is seen in more than a certain number of apps, it is considered to be a third-party library. And also, we can determine who initiated the connection, who did the validation of the certificate, as well as hijacking. And our data set also covers both regular Google Play apps and apps from Chinese app stores, with the rationale that prior work has also shown very distinct characteristics of both types of apps, such as permissions requested. And this also considers the large user base of the Chinese app stores. So we analyzed around 5,000 apps from Google Play, 3,000 apps from the Chinese app store. They're both run on 2 Pixel phones running Android 13. Before looking at the results, let's first explain what we mean by hijacking. So as I said, it's about someone's connections certificate gets validated by someone else unknowingly, and this is possible technically because most HTTP implementations in Android supports to set a global default for the class instance that does the validation. For example, if you call set default hostname verifier, the function you specify will actually validate the certificate of all subsequent connections. So this is what I mean by global. It's affecting any other parties in the same app, which is supposedly dangerous. You don't have to read this. This is a code snippet from an app, just to quickly give you a concrete sense that it is overriding this class trust manager's 2 methods, specifically check client trusted and then check server trusted, with the blank function. It's empty. This is just for logging. And then you can imagine how dangerous it could be. It's skipped. But the actual, who wrote the code, for example, the connection being verified for, is not aware of this. And please just refer to our paper for detailed statistics for the sake of time. But at the high level, we can already see the distinction between the 2 types of apps, specifically for both aspects. Apps with insecure connections caused by the validation issues and function override or validation function hijacking. It actually affects more than half of the apps from Chinese App Store, and it's much lower percentage for Google Play apps. And then for the hijacking, it's relatively similar. And then let's look at the attribution cases. So you can see the 5 combinations determined by who initiated the connection and who does the validation. There's an interesting observation here if you look at Google Play apps. So the first 2 cases, it's something validated by app code, something validated by app code. So you see somehow for Google Play apps, the insecure connections are mostly introduced by the app developer. In comparison, for apps from Chinese app stores, you look at the last 3 cases, especially in the one in the middle, almost 50%. It's mostly introduced by third-party libraries. You see, validated by library code, validated by library code, and the same applies here. So these boxes in red indicate hijacking because it's not validating its own connections. So this is an interesting observation. And again, some concrete examples. I'll just simply explain, for example, the third one. It's a connection of the app validated by library code. You see it's an app, something about nurse, but it's about to load an image. And this connection was validated by Tencent Bugly. So the ProGuard code before this connection was established. And there could even be race conditions depending on who called that set default function last. So in this example, you can find it in our paper. So it's really not deterministic. And then at last, of course, this is problematic, the insecure connections. So indeed, almost 90% of these insecure connections have sensitive information transmitted. We also implemented a phishing attack on a real app, not what we created. So we intercepted the traffic, replacing an ad with a phishing page. So this is a proof concept, but it's actually, it could be a real attack. Okay, so we can have some quick reflections on the findings. So specifically, I think it's about the root cause is about whether or when the default values, the default functions are retrieved before each HTTPS call. And then among those different HTTP implementations, only Google's fork of OkHttp does that. So that's more vulnerable. And we also did a manual analysis of other implementations. Supposedly, they could also be vulnerable, but not observed yet. Okay, at the very end, we think about potential future mitigation of the problem. So for example, this is actually working as designed. It is actually intended. For example, this is allowed by the Java programming language. You can overwrite. But do we need this flexibility with the threat model shift? So this is actually a threat model shift with multiple parties within a single app. And also, we contacted Google. You can see the details in the paper. I think what was actually proposed is actually introducing warnings in Android Studio so that the developer is warned, but it's not something enforced at runtime. And of course, optimally, hopefully, it will be properly enforced with the new privacy sandbox in Android so that there's no shared instance of the default functions between multiple SDKs. And you might be wondering, okay, what about the latest? Because our test was done on Android 13. We also tested additional devices and operating systems after the paper was finalized. And then we did observe the same vulnerability in Android 13. And it also covers many other versions of the system and even variants of Android. All right, thank you for your attention. I'm happy to take questions.